Well, I'm glad you were able to log on. My last student, he could not log on. I was hoping it wasn't something wrong with GoToMeeting.
Yeah, that's I'm really glad it's working.
Yeah, me too. I would hate to have it not working the night before finals.
Yeah, that would not
Suck
that would
for
not.
you, wouldn't it? So, all right, what are we doing tonight?
Um so to start I have there's a picture, but I think I can verbalize it. It's just a rectangle,
Okay.
and the width of the rectangle is x and the length is unknown. And it says three sides of a fence and an existing wall form a rectangular enclosure. The total length of the fence used is 240 feet. Let x be the length of the two sides perpendicular to the wall. And then it says write the area of the enclosures as a function of the length of x.
Right. Yeah, no, I had this same exact problem from my other student.
Right?
So this is what we're looking at. In other words, we only need to build three sides of that rectangle. And that's x. Let's assign a variable to that dimension, y, because we need a variable for a moment. That's x. What we're trying to maximize is the area, correct?
Correct.
So always start with that function, the area that, or the function you're trying to find the maximum of. Well, what's area equal to? From
Uh, Times y.
okay. Now, we also know some information about x and y that we can relate based on the fact that we have 240 feet or meters, whatever, of wood. What equation can I write regarding x and y and the number 240?
Y plus 2x equals 240.
Notice what that allows me to do. That's an independent equation. So that allows me to write y in terms of x. That's what y is. And now I can go down to my area function, the function that I'm trying to maximize, and I can make it all a function of x. It didn't do me much good when it was a function of x and y, but now I'm going to have it completely as a function of x by substituting for y.
Okay.
And that turns into what?
Negative 2x squared plus 240x.
What is that?
Parabola.
Correct. It's a quadratic. And it's a parabola. Does the parabola open up or down?
Down.
So it's a parabola, perhaps something like that. Okay? And this vertical dimension is a of x. It's the area, is what we're plotting here, as a function of x. So if we can find this point right here, we will have the x dimension that produces the maximum area. If x were less than that amount or greater than that amount, then the area would be less, right?
Right.
Okay, how do we find the only real coordinate we need is the x-coordinate of this vertex. They
Right.
didn't ask us what the maximum area was. They just said what dimensions should be used to maximize area. So when you have a parabola, how do you find its vertex?
Complete the square.
That's one way to do it. Probably not the easiest way. Since the x coordinate of the vertex is the only thing we need, then we should use this, minus b over 2a.
Oh.
And memorize that. And one way that it's useful to memorize that is, what's the quadratic formula? That's the first half of the quadratic formula. Right?
Right.
In other words, quadratic is minus b plus or minus the square root of the discriminant all divided by 2a. Well, what I call the first half is minus b divided by 2a. And notice how rapidly we're going to come up with the x coordinate. What's minus b?
Negative 240.
2a?
Oh, sorry, excuse me, Mr. Count.
Yeah. You okay, William?
Yeah, I'm
You need to take a little break?
Mr. Cowell, are you there?
Yes, I am. Is William okay?
Yeah, he's, so I don't know if you mentioned that he's sick.
Well, I kind of figured that, just from the background noise.
He's growing up, and he's got a fever, so.
Okay. Should
So
we?
he's trying to get through it here, but of course, he just threw up, so.
Okay. So,
All right.
should we call it a night?
Let's do, did he said there was just 3 left, and I don't know how many.
Do you want to try to finish?
No, he's still in the bathroom. I need to give him. Are you sure? You want to finish? Yeah. All right, Mr. Cowan, he's coming back. He's trying to power through this.
Okay.
All right. Give him just a minute, okay?
Sure. No problem. Have him take his time.
Yeah. Yeah, it hit him unexpectedly this morning, or last night.
It's rough.
Yep. Okay.
Rough doing this when you're feeling good. It's terrible doing it when you're feeling sick.
All right, Mr. Count. I'm so sorry about that.
No problem. No need to apologize. I hope you feel better. And you tell me anytime if you want to stop.
Okay, I think I should be okay.
I'm
But
sure
actually, I might, by the 30-minute mark, I think I might be okay. Depending.
like I said, any time you let me know, and we can end it if you're not feeling up to it.
Okay, thank you very much.
So, yeah, back to the vertex of this function. We've got a quadratic function here, which is our parabola, and to find the x-coordinate of the vertex, plugging it into minus b over 2a is really the simplest, most straightforward method. 2a is minus 4, so that very quickly gives you the dimension that x should be. 6.
Okay.
And then that's 60 up there. That leaves 120 for y. That totals 240.
Okay.
Okay. Now, I could have completed the square to figure out the coordinates of that vertex, because you can complete the square and put it into vertex format. notice one of the things that's going to happen if we go to complete the square here, I'm going to have a coefficient of 120 on the x term. I got to take half of that and square it.
Right.
I'm going to be dealing with really big numbers. So, and completing the square is harder anyway, especially compared to just minus b over 2a. So if I were you, I would definitely memorize that that is the x-coordinate only of your vertex of the parabola.
And if it's a horizontal parabola, it would be negative a over 2b.
Well, in this case, it's never going to be a horizontal parabola, not when you're dealing with word problems.
Right.
And that's the reason for that is that these are all functions. A horizontal parabola, you'll notice, is not a function. Does not pass the vertical line test.
Right.
So you don't usually ever end up, whenever you're dealing with word problems like this, I mean, this is actually a basic calculus problem is what this is. This is one of the starting word problems. They start you off with calculus. The only reason we can do it without calculus is because it happens to be a parabola. And a parabola only has one peak or one valley. It doesn't do something like that. Okay? That would be like a cubic or a quartic, and then we would need calculus. The moment your function is something larger than a quadratic, you can't solve it using the algebra that you've been taught. But as long as it is a parabola, then the only place you need to find is that vertex. And you do have the math for finding the vertex of a parabola or a quadratic.
Okay.
Okay? All right, what else do you got? Yeah, this thing, and it would not have mattered whether I solved this top equation here. I could have solved it for x and substituted for x and solved everything for y, and I would have gotten a y equal to 120, and I would have left x to be 60 and 60. So It doesn't really matter which variable you solve for. The key here is to determine the function that you're looking to optimize. And there is the function I'm looking to maximize. Okay? And you usually need one other equation that's independent that allows you to write this function in terms of one variable only. We don't really know how to graph that. That's not a quadratic. That's not a parabola. It only turns into a parabola or a quadratic when I figure out what y is in terms of x and substitute it.
Right.
I have a function of x. That's what a of x means. It means I'm only going to find x on the other. I could not have written this of a of x. This would have had to have been written a of x comma y.
Okay.
Because there's two variables on the other side, x and y.
Right.
All right. What else do you got?
So for this problem still, it says, what are the possible values of x that make sense in this problem?
Okay.
So is it asking the domain of the real solutions?
Pretty
Or
much.
not real,
In other words, does an
value.
x of 0 make sense?
No.
No, because then you'd have an area of 0. Does an x of 120 make sense?
Yes.
Not really. If I had 120, my y would have to be 0.
Oh, okay.
Notice the total amount of fence is 240. So
Right.
if x was 120, I would just have a straight line. I would have no area at all. So the effective domain for x is it has to be some number greater than 0, and it has to be less than 120. That's effective domain. Even though we have 240 feet of wood, like I said, it wouldn't make any sense to make x even 120.
Right.
You would have no area at all. Okay.
Okay.
Any other questions on this problem?
No, that's it for that one.
Okay. What else you got?
Identify the center, the foci, and the vertices of the following graph. 4x squared plus 3y squared plus 8x minus 6y equals 5.
What kind of figure is this? And you can tell by just those three terms. In other words, the two terms of the polynomial and the plus sign tells you what kind of figure it is.
Right. An ellipse.
Yeah. If you have an x squared and a y squared with plus signs in front of both, you have either a circle or an ellipse. If
Right.
the coefficients are not identical, it's an ellipse. If the coefficients are identical, no matter what they are, it's a circle. So the fact that one is 4 and the other one is 3 means we have an ellipse. Now, and I can't really tell by looking at this whether it is a vertical or a horizontal ellipse.
Right.
I won't know that until I get some additional information on it. In other words, if I can put it into ellipse general format, which is this is a little tough to explain. Ellipses, I can tell immediately if it's a hyperbola, whether it's a vertical or a horizontal. With ellipses, you kind of have to solve it, get it into the general format, and then whichever has the bigger denominator, it's either a horizontal or a vertical ellipse. In other words,
Right.
we know A has to be bigger than B, so whichever variable A ends up under, that is the major axis. Okay? So,
Right.
to put this polynomial into this general format, work me through it.
Group the x's and y's together and complete the square with both of them. Well, first, you should take out the 4 and the 3 from both binomials.
So the way I tend to think about these is I want to make sure that when I go from this step to this step, I have not changed anything at any point in the way. That's always how I do these. In other words, you're right, it's completing the square and factoring out that coefficient, but just make sure you do not change them from step to step. In other words, is this exactly the same as the previous step? And it is. Now, complete, in other words, this is the same as that.
Right.
Now, complete the square on the x's.
Add 1
And balance it on the other side.
by adding 4.
And with the y's.
Add 1.
The other side.
Add 3.
And now, we're getting closer to being in standard format. In other words, now it's 4 times what?
X plus 1 quantity squared.
Okay. Plus 3 times what?
Y minus 1 quantity squared.
Equals 12. What's the next step?
Divide both sides by 12.
So that's going to do that. Get rid of that 4. And it's going to do that and get rid of that 3, and it's going to leave 1 on the other side. Now, and this is really the first time I've been able to figure out which is A. Well,
Right.
this is A squared, this is B squared. I suppose that if I worked with ellipses enough, I would notice that it's always backwards from the original polynomial. In other words, whichever term has the greater coefficient, the B is going to be under that term, and the A is going to be under the Y. And it's always like that. I just hadn't noticed it before. So in a way, I could have told that this was a vertical ellipse by looking at those first 2 terms. All right. So they wanted the vertex, the center, and the foci,
and the vertices.
the vertices, and
Graph.
okay. Where's the center?
-1, comma 1.
I find it always quite useful to list A, B, and C. What's A?
2.
What's B?
√3.
What's C? C being equal to the square root of A squared minus B squared. So C being C being 1. I should have known that because that is a 30-60 right triangle, which will be the most important triangle you work with next semester when you take trig. And it has dimensions of 1, √3, 2. And we were looking at 2 here for the hypotenuse, √3 for one of the sides. The other side had to be 1. Now, we have everything. Let's graph it. Center is at -1, 1. And we know is a vertical ellipse. Now, I draw it like that even though I don't really know that it crosses the y-axis or the x-axis. In other words, I'm really grossly approximating it. Not going to change the coordinates I put on all of the vertices. What's the coordinate on the top major vertice?
-1, comma 3.
Good. And the bottom vertice?
-1, comma -1.
And the right vertice? Minor vertice. Yeah.
0, comma 1.
You're getting this down good. And the left vertice?
-2, comma 1.
And the top foci?
-1, comma 2.
The bottom foci?
-1, comma 0.
Yeah, we can see that I didn't quite draw it accurately, but that's okay. I got the vertical part correct, and I got everything labeled correct, and I came up with my labels based on algebra, not the graph. So that's all they wanted, right?
Yes.
Okay. What else?
A particular lake has enough food and water resources to support 3,500 trout. If there were 50 trout originally introduced into the lake, after 3 years there were 325 trout. How many will there be in the lake after 10 years? And it gives the equation. It's P of t equals C over 1 plus A times E to the negative B times T.
This is called a logistic function. And they tend to look like they're almost exponential. In other words, for a while, the trout grows exponentially like this. But because the lake is limited, it can't grow exponentially forever, and so it tends to flatten out. And there tend to be horizontal asymptotes and vertical, or two horizontal asymptotes on this type of function.
Right.
So the bottom one is probably y equals 0. It maybe could be y equals 50, but probably not. It's probably y equals, well, I'm not sure. But let's see if we can solve this equation. P of t being the population of the trout based on time. Okay, so let me erase my curve here so that I have room to write. So let's see. The C is the initial, and the initial was 50 trout, right?
Oh. I thought the initial was the limit.
No, the P of t is the population of the trout based on time. So I'm going to put 325. Oh, C, I think, is the limiting population. In other words, the numerator becomes 3,500. All over 1 plus. Did they tell you what A, B, and C were anywhere?
No, it did not.
They didn't?
No.
I'm going to have to get out my book. Hold on a second. Pretty sure that C, I think C is the limiting number, which was 3,500, right?
Correct.
All right, hold on a second. Logistic growth and decay, 267. Is actually a function that a lot of people don't deal with very frequently. Okay. So A, B, C, and K. Oh, no, hold it. Or A, C, and B are constants, and C is the limit to growth. Okay, so 325, or rather 3,500 is definitely C, and this is the population at any point in time, and so we know we got 325 trout at the end of 3 years. So now I know this much. Now I still have two variables, A and B. Hold on.
Is A the initial population?
Yes, I think you're right. I do believe that that's what A is.
I submit it's 50.
And that does allow us to solve for B. Hold on a minute. Let me just look at this one application we have. Hold on. Yeah, we actually give two different functions for a logistic in my book, and the one that you gave me was the second one. And they're actually a little different, oddly enough. But the second one, A is definitely the initial. So in our case, A is 50. And now that's enough information to solve for B.
Right.
And once we've solved for B, we know what C is, we know what A is, we'll know what B is, and then we can answer any question they want because we'll have the population as a function of time is equal to this logistic function, and there's only one variable in it, and that's T. So let's figure out how to solve this. How do I solve that equation?
Multiply both sides by 1 plus 50e to the negative.
By that denominator, okay? And that gives me, on the left side, 325 plus, what is that? 1750? What is 50 times 325? I think it's 1750.
16,250.
Math skills are 16,250. Makes more sense. And that's equal to 3,500, the number that's still left on the other side. Now what?
Now subtract 325 from both sides.
Okay, so that gives me 3,175. Gets rid of that. Now what?
Divide both sides by 16,250.
Gets rid of that. And now I have e to the minus b times 3 equals that ratio. Now what?
Take the natural log of both sides.
Which gives me minus 3b equals the natural log of this number.
And then divide by negative 3.
And again, we know that that number is negative, the numerator, because it's the natural log of a number between 0 and 1. So that's going to be negative, divide by a negative, b is going to end up being positive. And that's good because in our original function, we've got that negative sign in front of b again. So we want that to be negative always in the logistic function. That's negative. And so now, what did they want to know now?
What will the population be after 10 years?
Okay. So I'm going to go to this. Going to substitute 3,500 for C, 50 for A, the answer we came up with for B, and 10 for T. And that's going to give me all numbers. So, you need an answer, right?
Yeah,
All right, so here's what we're going to have. Population after 10 years, right?
correct.
Equals the 3,500 divided by 1 plus 50, still part of the equation because that's what they started with, times e to the minus natural log of 3150 divided by 16,250 all divided by 3 times 10. Whatever that number gives you is your population after 10 years. And clearly we needed to be a number less than 3,500, right?
Right.
What 3,500 means is that if you let this lake go for 100 years, its population would steady out around 3,500. Would never get much bigger than that. It's not a big enough lake to support more than 3,500 fish.
I got a really strange decimal.
What'd you get?
0.302944.
Well, that's pretty impossible also.
Right.
In other words, it grew from 50 to 325 in 3 years. So it grew by a factor of 6 in 3 years. At the end of 10 years, it's going to be up over 1,000 for sure. So my guess is that you made the same mistake that we both made 2 or 3 sessions ago in trying to do one of these. And so how did you get your denominator to be greater than your numerator? What do you get when you take the natural log of 3150 divided by 16,250 and divide it by 3? What's this become? All of it. Everything inside my parentheses, what does it become?
0.546897.
Okay, and then we got to multiply that by 10, so it becomes 5.468. And now we're taking e to the negative that number. So what is e to the minus 5.468?
0.004216.
0.004216. Going to multiply that by 50 and add it to 1. What do you get?
1.21078.
1.21078. So that's our final denominator. Now divide 3,500 by that and you'll get the correct answer.
2,890.7.
Yeah, and that makes sense.
Right.
Not the 0.7, but in fact, I think that you would want to round this off to, well, I don't know. You can't have 0.7 of a fish. So I wouldn't think that they would want you to round it off to the nearest tenths. They probably want you to round it off to the nearest full fish. So maybe 2891, I don't know. But kind of illustrates what can go wrong on these problems. I suspect it's just extremely difficult to get that into the calculator properly.
Yeah, it must be.
Or I'm trying to remember the mistake that I made without realizing it. I'm not even sure I ever figured out my mistake. I just kept adding parentheses, and eventually I got an answer that was the correct input, and the answer made sense. But this is one case where having that ballpark answer is really useful, because the first answer you came up with of 0.302 is not in the ballpark of answers. So the good thing is that it tells you made a mistake. The bad thing is it doesn't tell you where, but it's pretty easy to figure out where one would make a mistake in trying to come up with this number. It's going to be in evaluating this e to the minus that complicated log. Okay, so I'm not sure what the moral of the story is. Does your teacher teach you to do it this way, or does he have you turn this into a decimal number when you solve for b in the first place?
No, she, usually the directions on the quiz or test say use the exact value.
Good, I like that. And that's good, but it is a little problematic. For a final answer, she wants a decimal, right? Or a number of fish, not the exact 0.7 and so forth. So she does have you convert it to a number at the end of the problem. Well,
yes,
you can get by this other problem unless you have to show all your work. If you have to show all your work, then you're going to have to get it at least to this stage here that I just circled. But in terms of getting an answer out, it's so much easier if you do this more like one step at a time. In other words, like I had you do it. Evaluate what that natural log is, and you came up with 0.54. Then we multiplied it by 10. I don't ever remember dividing it by 3. Did we divide it by 3?
Yeah, we did. -3.
Okay. Yeah, okay, good. Certainly the answer we came up with is a very reasonable looking answer, but if I forgot to divide it by 3, I might come up with something just as reasonable looking. Because this function, this logistic function, is so complicated by having this very strange denominator that we might not have to make much of a change here, or changes we would make in this exponent for e might not affect the final answer by that much. It may came up with 2,500 instead of 2,890. So I could have made a mistake and not divided by 3, and we still might have gotten an answer that was in the ballpark. So you can't trust in ballpark answers totally. We are taking e to a negative exponent, and if you think of what that means, it means 1 over e to a positive exponent. So that number is going to be pretty small usually.
Right.
For these logistic functions. All right. Anything else needs said about that problem?
No, that's good.
Okay.
Thank you.
And she gave you this function over here, right?
Yeah, the equation.
But she didn't tell you what C, A, and B were, huh?
No.
Yeah, the thing I always remember is the numerator is the limiting growth, the 3,500. And really there's only one other thing that A could be. That's the initial starting amount. And then just like our exponential growth and decay equation, they're not that different. Notice the way we solve them are very, very similar. They're going to involve natural logs in their solution, and in fact they have this negative k, which is b. And these problems, every single one we've done, you had to figure out what that constant was as step one. Whether it's called K or B, called B with a logistic function, with a exponential decay, it's called K. But the first step is always to solve for that. And then once you've solved for that, then it becomes completely a function of time only. Good to go on that problem?
Yeah.
All right.
Actually, that should do it.
Okay.
That's the whole review. So.
All right. Well, we certainly don't need to go any further then. William, I hope you feel better, and
Thank you.
I have total confidence you're going to do very good on your final.
Thank you, Mr.
You've put in a harder effort than any other student I have, and you deserve to do good on it. So, good luck, and I will probably talk to you next semester when you tackle trig.
Yeah, for sure.
Okay, William. You have a good holidays, and feel better.
You too.
Bye-bye.